Find the consolidation coefficient, C sub v, in inches squared per minute. In this problem, a sample of soil is loaded into a metal ring and tested in a consolidometer. We've also been provided soil data, as well as testing results. The deformation, or displacement, of the soil was reported at various time intervals. The entire set of deformation data is listed here. The general equation for the time rate of consolidation is solved for the consolidation coefficient, C sub v. We'll use the soil data to determine the drainage height and the deformation data to determine the time factor, big T, and the duration of settlement, small t. Let's solve for the drainage height first. The initial height of the sample is 1.06 inches, but since the soil is doubly drained, meaning water can exit the sample through both the top and bottom of the ring, the drainage height is half the total height, or 0.53 inches. Next, we solve for our time factor and duration of settlement. Again, we see the entire data set. We'll generate a semi-log plot where the vertical axis is deformation, or displacement, in inches, and the horizontal axis is time, in minutes, plotted on a log scale. After the data points are plotted, we return to our time rate of consolidation equation. Our goal here is to find the time of duration, little t, it will take the soil to consolidate 50% of its ultimate consolidation. Knowing the average degree of consolidation, or U, is 50%, we can solve for the time factor, big T. When U is less than 60%, T is about pi times U squared divided by 4, where U is a decimal. When U is greater than 60%, T is solved using this second equation, where U is a percent. Since U is 50%, we'll use the first equation. The time factor is 0.197. To solve for the time it takes the soil to consolidate to half its ultimate consolidation, we draw a best fit line along the data points for a consolidation settlement and a second best fit line along the data points for a creep settlement. As an aside, some books refer to these two types of settlement as primary consolidation and secondary consolidation. So where these two lines intersect represents the displacement of the soil sample at ultimate consolidation. This ultimate consolidation is 0.025 inches. Next, we draw horizontal lines at the data points corresponding to the time of 0.25 minutes and 1 minute. Then, we add a third horizontal line above the two horizontal lines with equal separation as between the first two. This third line represents the displacement when no consolidation settlement has occurred. The displacement of the soil at 50% ultimate consolidation is determined by averaging the 0% and 100% displacement values. From the graph, we can determine the time it will take the soil to consolidate to 50% its ultimate consolidation by tracing a line horizontally right to the lab test data, then vertically down to the time axis. Our T sub 50 is 2.7 minutes. Plugging in our known values, we calculate the consolidation coefficient to be 0.020 inches squared per minute. Compared with our possible solutions, the answer is B.